The explanation of flight you learned in school, the one with the curved wing and the air speeding up over the top, is wrong. It's been wrong for over a century. And the scary part? Some pilots were trained using it too. Right now, there are 500,000 people suspended 7 miles above the Earth inside aluminum tubes moving at 500 miles per hour. The force holding every single one of them up there is real, it is measurable, and it is almost universally misunderstood. What you are about to see will dismantle the textbook explanation, rebuild lift from the ground up, and show you why the real physics of flight is stranger, more elegant, and far more beautiful than the myth you were sold. You have probably seen the diagram. A wing slices through the air. The top surface is curved. The bottom is flat. Two molecules of air approach the leading edge, and the story goes like this. The molecule that travels over the curved top has a longer path, so it must move faster to meet up with its partner underneath at the trailing edge. Faster air means lower pressure, according to Bernoulli's principle. Lower pressure on top, higher pressure on bottom. Wing goes up. Plane flies. Simple. There is just one devastating problem. The two molecules do not meet up at the trailing edge. They never have. High-speed wind tunnel photography proved this decades ago. The air flowing over the top actually arrives at the trailing edge far ahead of the air flowing underneath. It outruns its supposed partner by a wide margin. The so-called equal transit time theory is a complete fabrication. It was never derived from physics. It was invented as a convenient classroom story, and it stuck because it felt intuitive. Here is how wrong it is. If equal transit time were true, you could calculate the lift on a commercial airliner. The number you get is only about 20% of the lift actually measured. 80% of the force holding the plane up simply vanishes from the equation. And yet, this explanation persists. You will find it in children's science books, museum exhibits, flight school handouts, even some engineering courses that should know better. So if the most popular explanation is wrong, what is actually happening above your head at 35,000 feet? Forget molecules racing each other. Forget the shape of the wing for a moment. Start with something far more fundamental, Newton's third law. For every action, there is an equal and opposite reaction. A wing generates lift by pushing air downward. That is it. The air pushes back, and the wing goes up. Every airplane that has ever flown, from the Wright Flyer to an Airbus A380, works by deflecting a massive river of air toward the ground. Now here is where it gets interesting. The wing does not just shove air downward with its bottom surface like a hand out of a car window. The top of the wing does most of the work. As air flows over the curved upper surface, it follows that curve. It bends downward. This is called the Coanda Effect, and it happens because air is viscous and sticky at the molecular level. It clings to surfaces. As the air curves over the top and accelerates downward, it creates a vast low-pressure region above the wing. Think about this. On a Boeing 747 at cruising altitude, the pressure difference between the top and bottom of the wing is strong enough to support over 400,000 kilograms, roughly the weight of 60 adult elephants, using nothing but moving air and geometry. This low pressure is not a gentle suggestion. It is a violent demand. The wing is essentially being sucked upward into a partial vacuum of its own creation. And this is where Bernoulli's principle does play a role, but not the way your teacher described it. Bernoulli tells us that faster moving air exerts less pressure. This is true. The air over the top does move faster, and the pressure there is genuinely lower. But the reason it moves faster is not because of a longer path. It moves faster because the wing's angle and curvature force the flow to accelerate. Cause and effect are reversed in the textbook story. The shape creates the turning creates the speed difference, and the speed difference creates the pressure drop, not the other way around. So if the shape of the wing matters, but not in the way we were told, what actually controls how much lift a wing makes? The answer is the angle of attack. Tilt a flat plate into an oncoming wind, and it generates lift. No curved top surface needed. No airfoil shape required. A barn door angled into the wind produces lift. Poorly, inefficiently, with enormous drag, but it does produce lift. This is proof that the classic Bernoulli story cannot be the whole answer. This is exactly how the Wright brothers' first wings worked. Their airfoils were almost flat. The curvature was minimal. They flew because they understood angle of attack, not because they had perfected an airfoil shape. Every pilot learns this. In the cockpit, angle of attack is life and death. Increase the angle, and lift increases. But push too far, and the airflow over the top surface can no longer follow the curve. It rips away from the wing. The technical term is boundary layer separation, but pilots call it a stall. The low-pressure region collapses. Lift evaporates. And the airplane, all 200 tons of it, stops flying. It does not matter how fast you are going. It does not matter how powerful your engines are. Exceed the critical angle of attack, and the physics simply switches off. And this brings us to the most counterintuitive part of the entire story, the part that even many engineers get wrong. Because it turns out there is a hidden third mechanism creating lift that has nothing to do with pressure, nothing to do with Newton's third law, and it is happening right now on every wing in the sky. We will get there in a moment. Modern wings are designed as a negotiation between lift, drag, and structural integrity. Every curve, every twist from root to tip, every degree of sweep is a carefully calculated compromise. A supercritical airfoil on a modern jetliner is shaped to delay the formation of shock waves as airflow over the top surface approaches the speed of sound. The wing is not just generating lift. It is managing a localized sonic crisis across its entire span. Here is the part almost nobody talks about. A wing does not only create a pressure difference and push air down. It also generates something called circulation. Imagine the wing is sitting inside a spinning vortex of air, like a cylinder of wind wrapped around the airfoil. This circulatory flow adds velocity to the air on top and subtracts it from the air on the bottom. It is the mathematical backbone of the Kutta-Joukowski theorem, one of the most elegant results in all of fluid dynamics. Without circulation, the math predicts zero lift. With it, lift appears, precise and quantifiable. This circulation is not metaphorical. It is measurable. Every time a wing starts generating lift, it sheds a starting vortex from the trailing edge, a swirling tube of air that spins off behind the airplane and persists for minutes. You can see these vortices on humid days as ghostly white spirals trailing from wingtips. They are strong enough to flip a small aircraft that flies through one. So what actually keeps a plane in the air? Not one thing. Three mechanisms, deeply intertwined and inseparable. Newtonian deflection. The wing turns air downward, and the reaction force pushes up. Pressure differential. The curved, accelerated flow on top creates a low-pressure region that pulls the wing skyward. And circulation. A bound vortex system around the wing that organizes the entire flow field into a lift-producing pattern. No single explanation captures it all. The textbook tried to give you one clean story. Reality refused to cooperate. Flight is not a simple trick. It is an emergent phenomenon arising from the full complexity of fluid dynamics. And the fact that we engineered it before we fully understood it might be the most extraordinary part. Today, computational fluid dynamics can simulate every molecule around a wing. We can model turbulence at scales that would have been unimaginable 50 years ago. But here is what stays with me. We flew for almost 70 years before the scientific community reached consensus on why wings actually work. We built the machines first. The understanding came later. So the next time you are on a plane and you feel that push as the nose lifts off the runway, remember, you are not being held up by a simple diagram from a 7th grade science class. You are riding one of the most sophisticated interactions between matter and motion that humans have ever harnessed. And we are still learning how it works. Here is my question for you. What other everyday system do you think is widely misunderstood, something we all use but almost nobody can correctly explain? Drop it in the comments. Those are the topics that make the best episodes. And if this changed the way you think about flight, subscribing means you will catch the next one.